Hello everyone, and welcome to last section of this course, Data Prediction using Regression. In this section, we will learn about the different algorithms for data prediction, which include linear regression, random forest, neural networks, and regression trees. In the first video of this section, we will be performing linear regression, which is one of the most widely used techniques for data prediction. The stats package will provide us with the needed functionality for linear regression. R will load this package automatically during startup. We will be using the AutoMPG dataset to predict MPG based on cylinders, displacement, horsepower, weight, and acceleration variables. Okay, so let's get started. To perform linear regression, we will first load the caret package. Now, we will read the data using the auto command. Let's convert cylinders, which is a categorical variable, into a factor and appropriately rename the levels. Now we will set the random seed so that our results can match, and then we will go ahead and create partitions. Use the names command to print the names of the variables in the data frame. This will help us use appropriate variables in the linear regression model. Now let's go ahead and build the linear regression model using the LM function. The part of the command data is equal to auto followed by some argument value means that we want the model to use only the training data. We do not want to use number, model year, and car name corresponding to variables 1, 8, and 9 respectively. This is the shorter version of the command that we are executing. We could have included all variables, but that would mean having to explicitly specify only the required predictors in the formula expression. Now, note that even though one of our predictors, that is cylinders, is a factor and categorical variable, we did not generate dummies for it. The LM function takes care of this automatically, and the regression coefficients in the output represents this as well. Let's go ahead and print the value of the model variable. This will return basic results of our model with regression coefficients. Your results may differ slightly because of random sampling differences in creating the partitions. For a more in-depth analysis, the summary function will return detailed results about the model. As we can see, the residuals section shows the distribution of the residuals on the training data through the quartiles. The coefficients section gives the estimates of the regression coefficient. The second column, STD error, gives the standard error of that estimate. The third column will convert this standard error into a t-value by simply dividing the coefficient by the standard error. The column of PR followed by an argument converts the t-value into a probability of the coefficient being 0. The annotation after the last column symbolically represents the level of significance of the coefficient estimate by using a dot, blank, or few stars. The legend below the table explains what the annotation means. Generally, a coefficient is taken to be significant at 95% level of significance, and the same is represented by an asterisk symbol. The next section of the output shows us how the regression is performed as a whole. The residual standard error is just the RMS that is adjusted for the degrees of freedom. It represents the average deviation of the predicted value from the actual value. The adjusted R-squared value tells us what percentage of the variation in the outcome variable is indicated by the regression model. The last line shows the F statistic and the corresponding p-value for the whole regression. Now we will use the predict function to generate predictions on the test data. We can go ahead and compute the RMS error on the test data. we can now view the diagnostic plots of the model. Let's set up a matrix of 4 plots before calling the function. Finally, we will generate the diagnostic plots. Let's go through these plots in detail. The residual versus fitted plot helps us examine the residuals for a trend. In an ideal case, we would want this plot to be trendless and almost a horizontal straight line at 0. Our example shows a very slight trend. Next, the normal Q to Q plot helps us check the extent to which the residuals are normally distributed. This is done by plotting the standardized residuals against the theoretical quartiles for the standard normal distribution. Now, we can say that the normality condition is met if the points all lie close to the 45-degree line. In our example, we can see that the right extreme or at the higher values of the residuals, the standardized residuals are higher than expected and do not meet the normality requirement. We now come to the scale location plot, which is very similar to the first plot. The only difference is that the square root of the standardized residuals is plotted against the fitted values. This is used to detect whether the residuals exhibit any trend. Finally, the residuals versus leverage plot can be used to identify outlier cases that exert an undue influence on the model. In our example, the labeled cases can be candidates for removal. This brings us to the end of video 1 of section 5, where we learned about linear regression.